Okay then, morning everyone. Just to let you know, in case I didn't tell you before, so I've started putting up the tutorial question solutions on Moodle. So at the moment, just here under the number theory notes and solutions section, you can see there's solutions there now to the questions in chapters 1 and 2. Okay, and probably after this week I'll put up the ones to chapter 3, which is the current chapter on prime numbers and so on. Okay, and I'll just keep on updating that as we go through the course. Any questions before we begin? That's all. Questions or queries? Okay then. So let's think back to what we did last time. Last time, well, we introduced prime numbers last week. And we saw this nice proof that there's an infinite number of prime numbers. Okay, based on a proof by contradiction. This is a really nice proof. Certainly something every student of number theory should know and be able to recite, like words of the national anthem or something. Should be your national anthem in a way. So we know there's an infinite number of prime numbers, and that comes to us immediately from the definition of a prime number and the basic properties of divisibility that we have amassed up to now. I notice we did have to do those. For instance, in the middle of the proof, obtaining the contradiction, we make use of the fact that divisibility is transitive, and if a pair of numbers is divisible by something, then any linear combination of them is divisible by something. So we do make use in that proof a number of the little properties of divisibility that we spent so much time on developing in the first couple of chapters. So we know there's an infinite number of prime numbers. We knew straight away that the first theorem in this chapter that every number factorized into a product of primes, that really just falls out of the definition of prime numbers themselves. So if the number you're looking at isn't prime yet, by definition, it is possible to factorize it. So you factorize it, then you look at the numbers you're looking at. Are they prime? If yes, okay, you've reached prime factors. If no, one of them will factorize further and so on. So they keep on factoring. So everything can be factored into prime numbers, but what's not so obvious in that short description is that these factorizations are unique. And we really want that. We really want to be able to speak of the prime factors of and the prime factorization of a given integer. Okay? So we want this sequence of prime numbers that you have here, this collection of prime factors of a given number, we want to be sure that that's unique. Okay? And so there's essentially only one way to factorize a number. Okay, you might change the order in which you write down the 2 3s, the 11, and the 5, but you can't produce an essentially different prime factorization of 4 9 1. Okay, so that fact that the prime factorizations are unique, that makes up our fundamental theorem of arithmetic. Every integer factors into a product of primes uniquely. And you can even make the string that you write out, just the string of characters, you can even make that unique by insisting that the ordering from left to right of the prime factors be increasing. So the P1 is the smallest prime factor, say, P2 is the next smallest one. And then the actual string of characters here will be a unique factorization, and uniquely associated to n. We don't normally insist that it be so pinned down, but it is possible to do that. Okay, so that prime factorization was proved with the help of Euclid's lemma. I'm not going to redo the whole lectures last time, but just kind of quickly going over the main steps. Euclid's lemma, okay, this very important property of divisibility on prime numbers. We proved a more general form of it in the exercises to chapter 2. That was that if a prime number divides a product, a times b, then it must divide one of the factors, a or b. And by generalizing that to any number of factors, if p divides a product of n integers, a1 to an, then it must divide at least one of them. And that's Euclid's lemma. And that was the key step in proving that the factorizations were unique. We had an induction argument. So again, this is a case where we're seeing induction coming in. We stressed that in chapter 1, that induction is very, very important for number theory because the induction property is the characteristic property of the integers. The integers kind of look the same as lots of the other number systems. They possess the same algebraic properties, you know, the way the operations of addition and multiplication behave on them. But what really separates, what really clearly identifies the integers as opposed to the rationals or the real numbers is this property of induction. That you're able to inductively cover all the integers. And you can construct proofs about all the integers using this principle of induction. Prove it for a base case, normally n equals 1 or n equals 0 or something, some base case, and then you prove the inductive linking step. If it's true for one integer, it's true for the next one, then the principle of induction tells you then you prove it for every integer. Okay? And that's what we did for proving the FTA. Okay, so that about brings us up to where we were last time. And straight away there, so to continue here, we're going to look at just some consequences of the FTA and look at some of the arguments we can build up using this idea of prime factorization. So the first one there is exercise 3.1. Excellent. Exercise 3.1 is looking at the canonical forms of two integers a and b and asking us, is there a nice characterization of the greatest common divisor and the least common multiple in terms of those canonical forms, so those prime factorizations for a and b? Okay. What's the first one we're going to look at? So just to slightly rephrase the exercise slightly, I'm asking, can we characterize or describe the prime factorizations of the greatest common divisor of a and b and maybe the least common multiple of a and b in terms of those of a and b. So if you know the prime factorizations of a and b, do you then automatically know what the prime factorization of the greatest common divisor is, and similarly the least common multiple? Remember, the greatest common divisor and least common multiple, they're not two independent objects. If you know one, you automatically know the other. If you remember, we proved in an exercise that if you multiply these two together, you get the product of a times b. So they're locked together in relation to the value of the product of a times b. Well, to do this, this does have a nice answer, a nice characterization, and I have alluded to it before. So our prime factorization, so A we might think of as the product of primes pi, alpha I, and B, the product of primes qi to the beta I, product over I, Been a bit sloppy about where I starts and ends. Not really that important. Product over a bunch of primes, pi for A, product over another bunch of primes, qi for B. But what we'll need to be able to talk about is this set, capital P. And I'm going to say that this is equal to the set of primes P, such that P divides A or P divides B. So I've got one collection of primes for A and one collection of primes for B. I want to consider the union of them. Okay? So P, i.e. capital P, equals the union of the set of prime factors of A and set of prime factors of B. So inside capital P, we can find all the primes that divide A and all the primes that divide A, and none others. Yeah. So then what I'd like to be able to do is to have a nice expressions for the GCD of A and B and the least common multiple of A and B as products over this set, capital B. Now, we'll slightly adjust the expressions for A and B. So this is the product of P over alpha sub P, and B is the product over P, capital P, P to the beta sub P. So alpha P and beta sub P are allowed to be 0 now. See, because some of the primes appearing in this set, capital P, some of them will be factors of A, but not factors of B. Okay? And vice versa. Some of them will be factors of B, but not factors of A. So I'm slightly adjusting these prime factorization formulae so that I can allow the powers to be 0. So for instance, if we're talking about a prime which does divide B, but not A, then that prime little p will have a certain exponent over here, the number of times it divides into the integer b. But if that individual p does not divide a, then its exponent over here, and this expression will be 0. That will represent. Question there? Okay. Union of the set of prime factors of A and the set of prime factors of B. The union of those two sets. So I just had to slightly change the prime factorization. So it's not surprising that the greatest common divisor of A, B, and the least common multiple, it's not surprising that it's going to depend on the prime factorizations of A and B. But what I'd like to do is for us to arrive at exact description. It might help if we gave ourselves a bit of a non-trivial example. So the 495, which I think was a factorization in the notes, that was 2 3s, a 5, and 11. So that was 3 squared by 5 by 11. And let's say we have 5 and 11 and 2. What's that? 110. Okay. Now the GCD of those two and the least common multiple, well, we can construct those from their prime factorizations. Okay. So the greatest common divisor of 495 and 110, we'll be looking at these prime factorizations and looking, well, what's the commonality between? Well, there's 3's up here, there's no 3's down here. There's a 5 and 11 up here, and yeah, there is a 5 and 11 down here. So the 5 and the 11 are what's common to it. But if we're looking for the least common multiple, we want to write down a product of prime numbers which is a multiple of this one up here and a multiple of this one. And we want it to be the least one. So we have to write down a prime factorization that contains this up here and contains this, but doesn't contain anything else that isn't necessary for that. So it'll have to have a 5 and 11 in it, it'll have to have 2 3's in it, and it'll have to have a 2 in it. Just whatever it is, 2 times 495, which is 990. So what have I done there in general? Can we describe what we've done there in general? Both the GCD and the LCM, they're both given as prime factorizations over this same set of primes. Well, what exactly is the exponent? Hopefully we can have a formula for the missing exponent here, in both cases, in terms of the exponents attached to A and B. So just to be clear, for example, the prime 2 does not occur in 495. So if 495 is A and 110 is B, then the alpha 2 would be 0. Because we don't see a factor of 2 up here. So we do have 2 to the power 0 would be the way 2 occurs in the prime factorization of 495. And similarly, 3 is not down here, so the beta 3 would be 0 as well. So you could add on a power of 3 into the prime factorization of 110, even though there isn't a 3 there, if we allow that exponent to be 0. So what's the missing? See, for the greatest common divisor, we've only put down what's common to both. So we've only put down what's the same. But for the least common multiple, we'd have to put everything down. But not too much. We only put down each prime factor enough times so that it'll cover whatever occurs in 495, and separate question, whatever occurs in 110. So what are the two little functions I need? What function of the alpha p and beta p is the appropriate thing for GCD, and what is the appropriate thing for LCM? Yeah. So for here, we can neatly describe what I was doing on the board in this example here. We use the minimum. All right? Minimum, yeah. So is there a 2 in the factorization of the GCD? Well, we've got 2 to the power 1 in 110, 2 to the power 0 in 495. So if we choose the minimum exponent, namely 0, so there's a 2 to the power 0 over here in the factorization of GCD. You could add in factors of 2 to the 0 times 3 to the 0. You're effectively not adding them in. You're adding them in as a blank copy. Yes, that's good. So there's only one possible answer for the least common multiple. Minimum was the right answer for GCD. Just intuitively, what must the answer be? Maximum. The maximum. It has to be the maximum. It'd be strange if it wasn't. The maximum, because we want to, alpha p, we want to include a prime factor in the least common multiple. We want to include enough of it so that it's going to be a multiple of whatever's in 495 and whatever's in 110. Okay? So we basically have to include enough of it. We have to include every prime factor that does occur in either of them, and we have to include enough powers of that so that it is a multiple of what occurs in 495, and separately it is a multiple of what occurs in 110. Okay? So I've got 2 to the 1 because 1 is the maximum of 1 and 0, the 2 exponents on 2. I've got 3 squared because 2 square 2 is the maximum of 2 and 0. And then the 5 and 11 are both appearing to the power 1 because 1 is the maximum of 1 and 1 and 1. So it just gives us this very nice way of thinking of GCD and LCM in terms of the prime factorizations. So we have a very nice way. It's very nice because it's these nice, simple enough functions. The minimum of the 2 exponents or the maximum of the 2 exponents. So we have a nice way of expressing GCD AB and LCM AB in terms of, well, this is basically just what I was set out at the top, it's a characterization or a description of these two quantities in terms of the prime factorizations of A. Even though when we first introduced the greatest common divisor, we didn't have the language of prime factorizations or unique prime factorizations to hand. Okay? So that's kind of interesting as well. We were able to define the greatest common divisor and prove a lot of things about it before we had unique prime factorization as an available property. Okay? So this is one good way to think about the greatest common divisor. It's the kind of intersection of the two prime factorizations. But we also have the other way. A reminder, GCD of AB, this is the other characterization that you should have to hand about it, is the smallest possible, the smallest positive linear combination of A and B. And that's an interesting description of it, characterization of it, because it doesn't make any reference, it doesn't make any explicit reference to factors or divisors or prime factors. So it really does seem, on the face of it, two kind of very different descriptions of the greatest common divisor. Of course, they're fundamentally linked, and really they're fundamentally kind of expressing the same concepts, but it is two different ways of thinking. Okay, any questions based on that, or queries, or clarification? Okay, so we should look on a little bit more and look at some more consequences that we have here in the notes. Let's go back to the screen. The existence of irrationals here. Now, this argument should be familiar to you. I hope you've seen this before, because it was certainly known to the ancient Greek mathematicians. This idea that the square root of 2 is an irrational quantity. We can give a nice argument for this using the language of prime factorizations, and indeed we can generalize it to, I mean, there's nothing inherently special about 2 really here. We can prove a very similar result about every possible integer that you might take the square root of, or even a higher root as well. So you can imagine ancient mathematicians, would have developed some theory of numbers or surrounding counting numbers, the integers, first of all. Then they would have got into measuring things accurately for building whatever constructions they were doing. And then they would have discovered, began to talk about quantities like halves and thirds and quarters, and getting more and more accurate all the time. And maybe their theory of numbers built up, and they thought that the counting numbers and fractional quantities was all that there was. So this was probably a big deal way back then, when this simple number, and it is a simple number in a sense, the square root of 2, because it arises very naturally. It arises, of course, when you build a rectangle, and you make sure you've got a nice vertical right angle here, and both sides of the rectangle are length 1. Of course, we all know the length of this quantity there, the hypotenuse, then will be square root of 2. So it's a quantity that arises very naturally in geometric constructions. But it's got a certain weirdness about it, in that it isn't a rational number. You can't represent this number as a fraction of integers, no matter how large you make the denominator, no matter how accurate a rational number you care to construct. You'll never be able to exactly capture this quantity. And we can prove this very nicely using our language that we built up here. So to prove by contradiction, you can tell that because it says suppose on the contrary here to start. So we suppose it was rational. Well, if it was rational, we could express it like this: root 2 is a over b, where a and b are integers, and we'd suppose that the fraction is simplified as much as possible. So a and b have no greatest common divisor, apart from 1. They did have a non-trivial common divisor bigger than 1. We could divide it out of each of them to simplify the fraction there. Okay? So this is the rational fraction quantity for root 2 using the smallest possible denominator. Okay? And smallest possible numerator as well. So we suppose we have that. Of course, this is impossible to have because we're going to prove that you can't do this, but we pretend we have this for the moment. Well, if we had this, then straight away we could get to this nice equation here. B squared times 2 is equal to a squared. And that's an equation amongst integers. 2 is an integer, and a and b are assumed to be integers. We've got b squared times 2 is equal to a squared. And then we just start examining the divisibility properties of the two quantities on either side. The most obvious thing that stands out is there's a factor of 2 here. Okay, so 2 divides the left-hand side. 2 is a prime number, isn't it? First prime number. So 2 must divide the right-hand side. Okay? 2 divides the left-hand side, it must divide the right-hand side. The right-hand side, a squared, is a product of two numbers, a times a. Euclid's lemma about prime numbers tells us, well, the prime 2, then it must divide one of them. It must divide either a or a. That means it divides a. It's about the same. So 2 divides a. But then on the right-hand side, you've got a squared. So there must be at least 2 factors of 2 on the right-hand side. Yeah? 2 divides a. Well, a is there twice, so actually there's at least 2 factors of 2 on the right-hand side. Here on the left-hand side, we can see one of them. So there must be at least one more factor of 2 on the left-hand side. So 2 divides b squared as well. B squared is a product of two numbers, b times b, so 2 divides one of them, i.e. 2 divides b. So 2 must divide a and it must divide b. But that means the greatest common divisor of a and b is at least 2. So 2 is a common divisor. But we just assumed a minute ago that it was only 1. So we've wrapped around our brains, we've contradicted ourselves. So either the universe is utter chaos and there's no distinction between true and false, or we made a mistake. And of course we did make a mistake. And the mistake we made was at the very beginning, where we assumed that this was possible. Okay. It cannot be, because if it is possible, it forces a contradiction on it. Okay. So it's not possible to express the square root of 2 as a over b. Okay. Where a, b are integers. So root 2, although it arises very early on in geometric constructions, it's a very natural quantity to think about in that sense. It has this weirdness about it that you cannot capture it using a fraction, no matter how accurate you make your fraction, no matter how large the integers are that you allow in the numerator and denominator. Okay? So it's quite elusive. So these irrational numbers are elusive. They require, in a sense, infinite amount of information, in a sense, to describe them. Okay. Okay, any questions about that? You might have seen that proof before. That's a proof that's shown very easily. But at least we see now how those number theory concepts of divisibility and prime factorizations allow us to give a very rigorous version of the proof. We are very confident in that conclusion now because we've proved in detail all the properties of divisibility and prime factorizations that are used in that proof. It is an argument that's rolled out and told to people, and it is quite an accessible proof and argument because everybody has these good intuitions about divisibility. But nevertheless, we've really nailed it down. Now, straight away we can generalize. Was there anything special about 2 back there? No, not really. The same argument, more or less, can work for any integer n. Now, we're not claiming here that the square root of every n is, of course, is an irrational number. There are plenty of numbers which have perfectly nice square roots, 25, for instance, 36. Okay, these square roots are 5 and 6. So sometimes we see numbers that have integer square roots. They're already squares. They're square integers. 5 squared, 6 squared. But if that isn't the case, if the number isn't obvious, if the square root of n isn't obviously a rational number, it's obviously a rational number in the case where it's an integer. If that isn't the case, then it has to be an irrational. So when you take the integers and you apply the square root operation, you either end up in the irrationals, which you could indicators are less the rationals, or you end up back in the integers as well. So either you have a very nice square root, namely another integer, or you've got one of these weird square roots, and irrational. Okay, so I'll leave that proof to you as an exercise. It's basically replaying that same argument there, but with n in the place of 2. And to just talk carefully about, well, maybe sometimes it is an integer. But if it isn't an integer, if it doesn't qualify as an integer, then it qualifies as an irrational. And in fact, you can also generalize it away from square roots as well. It actually works for any kind of a root. Cube roots, fourth roots, fifth roots, fractional roots, rational roots. Okay? So that theorem can be generalized quite a bit. Any comments on that? Remember, sorry, just to emphasize, square root is a very natural operation. Okay? A natural operation. Natural in the sense that it's all over the study of geometry. Why? Because of the distance formula. If you're referencing points on a Cartesian grid, points A, B, points C, D, what is the distance between the points? It's the square root of the sum of squares of the differences in the respective coordinates. Okay, so squaring and square roots are very natural operations. They're not some weird artificial operation that we're carrying out. They arise so naturally in geometry. So if you want to talk about the distance between 2 points that are referenced on a Cartesian grid, then you're squaring and square rooting all the time. Okay then. Now there's then a section here at the end of chapter 3 called Established Results and Conjectures concerning primes, and this is just showing some of the further reaches of number theory in a sense, some of the famous results and famous conjectures, famous unproved results. There's a function pi. So this is a use of pi which has nothing to do with the circle, or nothing explicitly to do with the circle. Pi of x is just used because it's the Greek version of p. Pi of x is the prime counting function. So if you evaluate it at a real number x, it tells you the number of prime numbers that are less than or equal to x. It's just this function that counts the prime numbers. And the prime number theorem is a famous result which establishes the so-called long-term behavior of pi of x. Now I'll have a look at that in a moment. I'll show you some interesting plots. It says that basically, asymptotically, the value of pi of x is approximately x divided by log x. Okay, so the number of primes less than an integer x in the long run eventually is approximately converging to, relatively converging to, the quantity x divided by log x. So when you take the limit of the ratio of them, the limit of the ratio of them converges to 1. Okay, so that's the prime number theorem. And you're probably, I'm sure you've heard of some of these other famous results. There's our famous conjectures. There's the Goldbach Conjecture, saying every even integer greater than 2 can be written as the sum of 2 primes. This has been verified with computer search to like even numbers of gigantic size. And all the time, it seems it's possible, given any even number, you can find 2 primes that add together to get that even. Okay? So it's a very apparent result. It's confirmed everywhere by experimentation, but the proof that it's always true eludes us. Okay? Similarly, the twin prime conjecture. When you look at the sequence of primes, you seem to keep seeing examples of primes which are 2 apart. So a prime number p, where p plus 2 is also a prime number. And that's the closest that two prime numbers can come. Okay? Because remember, most primes after 2, all primes except for 2 are odd. So the very next number after prime number is going to be an even number. So it's obviously a composite number. So the next prime number after p that might possibly be prime is p plus 2. The twin prime conjecture says that this happens infinitely often. Again, we don't have a proof of that. We have numerical evidence of it in that we have examples of very, very, very large prime numbers, p, for which p plus 2 is also prime. But attempts to prove it have so far, proved impossible. So on that note, and coming back to the prime pi function, let's just have a look at the prime pi function. So there's a command here in Sage, plot prime pi, 1 to 100. This is what the prime counting function pi looks like when you plot it. It's called the staircase function. It's counting. See, x is the argument along here. And every time we encounter a prime number, it jumps up one click. It counts it. So this is the prime number 2. Here's the prime number 3. The next prime is 5. Yeah, and then you got 7, and then that's 10 there. So then 11 is the next prime. So every time we see a prime number, we jump up 1. So it's a staircase function. Okay? So it's what this counting function is like. But you wouldn't be happy if someone built you these stairs because they're very uneven. Sometimes the steps are very narrow, sometimes they're very wide. See a couple of points here where we've got unusually wide steps. And what are those unusually wide steps? Those are places in the integers where you can't find a prime number. Yeah? Because all the time, from here all the way up to here, if we pass through 10 or 20 numbers, none of them were prime numbers. So that's those very wide steps. The very narrow steps, places where it's very hard to get your foot in, are the twin primes, where the thing jumps up to start a new step, but then immediately has to jump up again when it meets a twin prime pair, and p plus 2 are both prime numbers. So talking about the stairs in this, the steps in this function, the twin prime conjecture, the thing we suspect is true, but we don't have a proof of, is that infinitely many times we get these extremely narrow steps. But even though it seems a kind of similar question, talking about the wide steps, we can prove something about that quite easily, quite immediately. Which is what we can just do in the 10 minutes left to us. And this is one of the aspects that makes number theory and mathematics, I guess, kind of interesting. We've two very similar sounding questions or statements here. One of them is easy to prove, because we're going to do it now on the board. And one of them is frustrated mathematicians all around the world for like at least 100 years. So what am I talking? Yeah, so the steps in pi of x. So the twin prime conjecture says infinitely often we have narrow steps, i.e. primes n and n plus 2. Okay, so the staircase jumps up 1 when it meets n, and then it has to jump up immediately again at n plus 2. So it's a very narrow step. That's called the twin prime conjecture. Now, not much progress was made on that for quite a few years, but in 2013, an American Chinese mathematician who works in America, Chinese-American guy, he made some good progress. And he proved that infinitely often we get, he was able to prove that infinitely often we get narrow steps of width at most 70 million. So infinitely often we see narrow steps of width at most 70 million. Now, of course, the twin prime conjecture says the width is 2. But that was the first successful proof that infinitely often narrow steps of any particular size occurred. Okay. And it's since been improved since by, well, if you look up, there's this online collaborative mathematics projects called the Polymath. Two of the main names is Timothy Gowers, who's a British English mathematician at either Cambridge or Oxford, I can't remember. One of those. And Terence Tao, who's an American. Terence Tao. They've since improved it down to about 246 or something. These people and other people working on this big collaborative online maths project have taken that initial narrowness measure of 70 million and reduced it down using improving Zhang's methods and adding some other methods. I've been able to show that it's down to 246. But we need to push it down to 2, and that seems impossible, or seems very hard. So that's conjecture. So that's something to aim for in the future for all of you. Make your name. So those narrow steps, but wide steps. So wide steps are like these sections here, where prime numbers are not to be found. Okay, so wide steps. The statement here is infinitely often we see arbitrarily wide steps. Or maybe even forget about the infinitely often bit for a moment. But just the statement, we see arbitrarily large steps. So we can see some steps here, they've got length about 10 or 20. If you look at the scale on the x-axis. But what about if I ask, well, is there a step of width 100? Is there a step of width 1,000? Is there a step of width 70 million? That's the question. Arbitrarily means we can find steps of wideness however wide we want. Okay. So these are regions, i.e. regions in the integers where no prime numbers occur. Okay, that's when you've got a wide step. You've got a region in the integers like from here to here, and there's no prime numbers in there. Then another one comes along, as it must, because there's infinitely many prime numbers. So the staircase does keep going up and up and up and up. Like if you're tired of climbing stairs and you just want to walk flat along, can you be sure that a region of width 1,000 is going to come and you won't have to step up? You'd just be walking along the flat. It'd be easier. Well, see, on the one sense, it seems a very similar question to this one, which is extremely hard to answer, the twin prime conjecture. But in another way, like I've got enough room here to prove it. We've got enough room to prove it. We've only got 4 minutes left, so it can't be that hard. So so what are we looking for? i.e., we want some number n plus 1, n plus 2, n plus w for wideness, to all be composite. That's what we're searching for. Searching for a sequence of adjacent integers, so n plus 1, n plus 2, so they're all beside each other, n plus w to all be composite. And then the question, can we do this for any w? Question. Now, if we want to prove they're composite, we have to prove that they're not prime, i.e. that they have at least, that they have some genuine factors. Everything has the factors 1 in itself, but they're not interesting. We want to see, prove some way to show that all these numbers in this list have non-trivial factors. But the question is, what factors are they going to have? I'll write in a few more. N plus 3, N plus 4. Where in the world are we going to find factors for all these numbers? And the answer is they're kind of staring us in the face. The only possible numbers that there are around, and so therefore they have to be the key to the thing, are these numbers 2, 3, 4, etc. Can we arrange it so that all these numbers are composite? And if you're looking for a factor of n plus 2, there's a 2 floating around, maybe we can find a factor of 2 for this. If there's a 3 already floating around, maybe we can show that there's a factor of 3. There's a 4 already floating around, maybe we could ensure that this is divisible by 4 by showing n as a factor. So thinking about this leads us to the idea of factorials. Okay? If we consider the number, basically consider W factorial, the width we want. If we consider the factorial of that, you see that as factors. What kind of factors does a factorial have? Well, factorials by their construction have lots of factors. 2 divides it, 3 divides it, 4 divides it, 5 divides it, 6 divides it. All of the integers up to W divide W factorial. So W factorial plus 2, W factorial plus 3, W factorial plus 4, all the way up as far as W factorial plus W. These are all composite numbers. Okay? Because this one, divisible by, so this one is divisible by 2. This one is divisible by 3, because 3 divides 3 and 3 divides W factorial. 4 divides that, 5 divides the next one, and finally W divides W factorial. So what we've got there is a list of consecutive integers. They're all one beside the other. This is the first one, W factorial plus 2. That's the next one, plus 3, plus 4. So they're all neighbors on the number line. But none of them are prime numbers. They're all composite numbers. So these form a wide step. How wide is the step? You see, if you start counting at 2, you finish at W. So there's W minus 1 things there. So this is the step of width W minus 1. That's okay. That effectively proves we can find steps of any given width. If you want a step of a width 1,000,000, you will find it in the staircase function if you go along to 1,000,001 factorial plus 2. So if we could extend this graph out to 1,000,001 factorial plus 2 on the x-axis, there's probably not enough room in the universe to do that. But if we could, from that point on, the next million integers are composites. So this graph will not step up until it's got to the very end of that run of infinite integers. Then the next step up is going to come sometime after that, whenever it encounters the next prime number after that. Okay. So, and the fact that these steps occur infinitely often, well, if you take any multiple, you see the same thing as this happens at the factorial of 2 times W, the factorial of 3 times W. So this wide step can be translated, shifted any amount up the number line. Okay. So infinitely often we see arbitrarily, i.e. as wide as we want, arbitrarily wide steps. That can be proved just there. But the twin prime conjecture says infinitely often we see the narrowest steps possible. On the face of it, maybe a very similar sounding question, but a much harder one, and one that's driven a lot of advanced number theory research over the years. Attempts to prove. Okay, we better finish just there. The number theory tutorials this Friday